Okay, so it's a mystery story, so let's begin. It was a dark and stormy night. And Einstein had just developed his general theory of relativity in 1916. And an interesting time, because he had developed that theory, which was the first theory of not just how objects move through space, but how space itself could expand and contract and be dynamical. A remarkable theory that told us that space curves in the presence of matter. And it was beautiful, and he kind of knew it was correct. But at the time, it disagreed with observation, which used to bother physicists in the old days. And the observation was that the universe was static and eternal. That was the conventional wisdom in science at the time, that the universe had been around forever and would be around forever. And his theory didn't agree with that, because his theory of general relativity suffered from the same problems that Newtonian gravity suffers from. Gravity sucks. It always pulls, it never pushes. And if you put stars and galaxies out there, they will not just stay there. Gravity will produce a universal attraction that will pull them together. And so he tried to figure out what to do, and he was able to change his theory slightly, consistent with the mathematical symmetries that allowed him to develop it. So I want to just show you how he did this. So I have his equations, which is a good thing to do at 9:45 in the morning or whatever. But I do have them in a user-friendly fashion here. Okay. This is for the biologists. No, I'm just joking. So it's not completely facetious, because the left-hand side of Einstein's equations tells you about the geometry of the universe, how things are curved in the presence of the source of curvature, which in this case is the energy and momentum of the universe. So that's fine, and in fact I'm a theoretical physicist, so I have to write the actual stuff, the Greek letters. That's much more illuminating to you, I'm sure. So this was the theory that didn't work, that explained the universe we didn't live in, or so he thought. And so he was able to change it a little bit by adding an extra term to the left-hand side, which he called the cosmological term. This term on the left-hand side would produce a small repulsive force throughout empty space, so small that it wouldn't affect the Newton's laws, which of course describe beautifully, or developed in fact to describe the motion of the planets around the sun, and you wouldn't want to destroy that. So small you'd never measure it in the solar system, but it could build up on the scale of galaxies and hold galaxies apart. And so that's how he thought he'd save his theory. Now, shortly after he introduced this term, it became clear that it was a problem. And in fact, here's a postcard I got when I was on leave once in Switzerland, in Zurich. And it's from Einstein to Hermann Weyl, who's a very famous mathematical physicist. And it's in German, and some of your German is better than mine. But this basically says, it's already 1923, and he's already saying, if you get rid of a quasi-static universe, then out with the cosmological constant. Because he realized that if the universe is really expanding, which is what we now know, and I'll talk to you about how we know that, then you don't need a cosmological constant anymore. If the universe is expanding, gravity can be universally attractive and just slow the expansion. And the big question of 20th century cosmology became, is there enough gravity to stop the expansion? How will the universe end? Will it end with a bang or a whimper? Will it end with a big crunch, the reverse of the Big Bang, or will it expand forever? In fact, and that's the reason why I, as a particle physicist, got involved in cosmology, because I wanted to be the first person to know how the universe would end. It seemed like a good idea. And you'll see where that came from. But anyway, so in 1923, Einstein said, you know, I wish I hadn't put it in, and threw it out, but it was really not 1923, but 1929, when we really knew the universe was expanding. And this is the person who convinced us. This is someone, and I always say this, so some of you may have heard me say this before, but it's true. This guy always gives me faith in humanity. This is Edwin Hubble. And he began life as a lawyer and became an astronomer. And so there is hope. And he made many discoveries, and I think because I'm a little short of time, I won't talk about the biggest, one of the ones he made, but the biggest one he made, of course, was the discovery that the universe is in fact expanding, and it changed everything. And this is what he discovered. Now, these are not sperm, these are galaxies. These are, again for the biologists. So our galaxy is here, and when we look out, we see what he discovered was that all other galaxies are moving away from us on average. And those that are twice as far away are moving twice as fast. Those that are 3 times as far away are moving 3 times as fast, etc. And so, and we codify this saying velocity is proportional to distance. And now, what does this tell you? Okay. Well, it obviously tells you we are the center of the universe. Okay. And actually it doesn't. And in fact, my wife reminds me of that on a daily basis. And it really means is that the universe is expanding uniformly in all directions. Now, why does this ridiculous observation that where everything is moving away from us tell us that? And I've spent a lot of time trying to think of different ways to explain this, none of which have been particularly satisfactory, but I think the only way to understand it is to get outside the universe. We're in California, it's easy to do that here, but let me do it this way. Here's a universe that's two-dimensional, and that you can stand outside of, and I put the galaxies at nice uniform distances here, and again here, and you can see at a later time the universe is bigger. The galaxies are a little bit further apart. So if you were standing outside of that universe, it'd be obvious that it was expanding uniformly in all directions. Now, what would you see if you were on that universe? Well, just pick a galaxy, any galaxy, and the way we could figure out what you'd see from that galaxy is to superimpose this image on top of this one, placing this galaxy on top of itself. Okay, what do you see? You see precisely what Hubble saw. Every galaxy is moving away from this galaxy. Those that are twice as far away have moved twice the distance in the same time. Those that are 3 times as far away have moved 3 times the distance. And it doesn't matter which galaxy you're on. Everywhere you see the same thing. Everywhere you think you're the center of the universe. So depending upon your mood, either every place is the center of the universe or no place is the center of the universe. It doesn't matter. The universe is expanding. And that really did change everything. And by the way, it had profound religious implications, at least. As some of you may know, that in response to this and other things, the Pope at the time gave an encyclical that science had proved Genesis. And the interesting person, the first person to actually show there had to be a Big Bang was a Belgian priest who was also a physicist named Georges Lemaitre. And the really interesting thing about Lemaitre is when the Pope said that, Lemaitre wrote him a letter and said, "Stop saying that." Just really amazing for a priest, because he said this is a scientific theory. You can take it if you believe in God and believe in Genesis to validate your beliefs, but you can also take it to mean that in fact the laws of physics take us right back to the beginning of time without God. What you take from it depends upon your religious and metaphysical beliefs, but whatever you say, the Big Bang happened. And I think that's if we could just convince a lot of people of just that simple thing, that the universe is the way it is, whether we like it or not, I think we'd overcome a lot of problems in this country, and I have to waste far too much time on that. But anyway, okay, but this is a science talk, although I'll throw in little bits of commentary throughout, I suppose. This is something that I wrote a whole book about, and someone asked me yesterday why I wrote that book. Because it is the most poetic thing I know about the universe. Richard wrote a great book called, what's it called? Our Ancestors? What's it called? Ancestor's Tale, yes. I wanted to make sure I got that right. And I wrote a book that was a different ancestor's tale. It was called Adam. But the amazing thing is that every atom in your body came from a star that exploded. And the atoms in your left hand probably came from a different star than your right hand. It really is the most poetic thing I know about physics. You are all stardust. You couldn't be here if stars hadn't exploded, because the elements, the carbon, nitrogen, oxygen, iron, all the things that matter for evolution weren't created at the beginning of time. They're created in the nuclear furnaces of stars, and the only way they can get into your body is if the stars were kind enough to explode. So forget Jesus. The stars died so that you could be here today. Okay? And anyway, this is great. Okay, great. So let's go back to Einstein. Einstein had this cosmological term. He said, "I was my biggest blunder. I want to throw it out, get rid of it." But the problem is you can't get rid of it so easily. Because using the miracle of modern mathematics, you can rewrite that equation. And now this is a small step for a mathematician, but a giant leap for a physicist. Not because it's that hard to put this term over there. Most of us could do that. But because it now represents something very different when it's on this side of the equations. Here it was somehow a geometric quantity. When it's here, it looks like a new contribution of the energy and momentum of the universe. What could contribute a term like this? And we know the answer. Nothing. By nothing, I don't mean nothing, I mean nothing. If you take empty space, and that means get rid of all the particles, all the radiation, absolutely everything, so there's nothing there. If that nothing weighs something, then it contributes a term like this. Now, that sounds ridiculous. Why should nothing weigh something? Nothing is nothing. And the answer is nothing isn't nothing anymore in physics. Because of the laws of quantum mechanics and special relativity, on extremely small scales, nothing is really a boiling, bubbling brew of virtual particles that are popping in and out of existence in a time scale so short you can't see them. Now again, that sounds like philosophy, like counting the number of angels on the head of a pin, or religion, or something useless. I shouldn't say, Dan Dennett is here, I shouldn't say philosophy is useless, but anyway, he's also a friend. But the point is, we can't measure virtual particles directly, but we can measure their effects indirectly. And in fact, they're responsible for the best predictions in physics. Here, by the way, is actually an animation that was shown at the Nobel Prize ceremonies about 5 years ago by a friend of mine who happened to win the Nobel Prize for developing the theory that produced this. This is the space inside of a proton, the empty space inside of a proton. Not where the quarks are, but the empty space between the quarks. And this is an animation, but it's an exact animation coming from physical calculations. This is what the space looks like. Now, how do we know that? Well, there are a lot of reasons, but one of the things are, it turns out most of the mass of the proton comes not from the quarks within a proton, but from the empty space between the quarks. These fields popping in and out of existence produce about 90% of the mass of a proton. And since protons and neutrons are the dominant stuff in your body, the empty space is responsible for 90% of your mass.